In this video lecture, we will see chapter 5 Principal Stresses and Strains. Topic is derivation of shaft subjected to combined bending and torsion, and marks is 9 for this derivation in SPPU syllabus. So, we will see this derivation thoroughly. First, consider a shaft subjected to the bending moment M and twisting moment T. That means this shaft is subjected to both bending and torsion. Bending moment by using bending formula. We had seen in our previous chapter bending and shear stresses bending formula. So this formula is M by I is equal to sigma by Y is equal to E by R. This E is nothing but the bending moment, I is moment of inertia, sigma is stress, Y is distance between neutral axis to elemental strip, distance between neutral axis and elemental strip, and E is modulus of elasticity, and R is radius of curvature. Radius of curvature. So here in this derivation we will only use this M by I and sigma by Y. So M by I is equal to sigma by Y. Therefore M is equal to sigma this I multiplied to this side, sigma I divided by Y, and here Y is R. In this derivation Y is equal to R. Distance between neutral axis and elemental strip distance is that radius of shaft here in this derivation. So from this equation sigma is equal to My by I. M multiplied by Y and Y is nothing but the R. My by I sigma is equal to M multiplied by R by I. So this is bending stress. Now we had also seen twisting formula or torsional formula in our chapter 3 torsion. So that formula is T by J is equal to G theta by L is equal to tau by R. Torsional formula is T by J is equal to G theta by L is equal to tau by R. Now second step is twisting moment by torsional formula. Torsional formula is T by J is equal to G theta by L is equal to tau by R. This T is maximum twisting moment, J is polar moment of inertia, G is modulus of rigidity, theta is angle of twist in radian, tau is shear stress, r is radius of shaft, and L is length of shaft. So this J is, what is J? Polar moment of inertia, and the polar moment of inertia is the plane area with respect to an axis perpendicular to the plane of the figure is called as polar moment of inertia. Polar moment of inertia definition is the moment of inertia of a plane area with respect to an axis perpendicular to the plane of the figure is called as polar moment of inertia. J is equal to Ixx plus Iyy, and for solid shaft it is pi d raised to 4 by 32. And we also see this shear modulus or modulus of rigidity is shear stress upon shear strain, capital G. So in this derivation, we will only use T by J and tau by R. Remember this. So T by J is equal to tau by R. T is equal to tau J by R. T is equal to tau. This J is polar moment of inertia and it is 2I. 2 into moment of inertia Ixx plus Iyy. Therefore, tau is equal to TR by 2I. This is shear stress and this is bending stress. Now, if sigma is normal stress and tau is the shear stress, the principal stresses are given by sigma is equal to sigma by 2 plus minus under root of sigma by 2 square plus tau square. So, substituting this one sigma and this tau shear stress, bending stress and shear stress in this equation 3. So take common this r by 2I square, and the square root of r by 2I square is r by 2I. And this is remaining m square plus t square. So see, this r by 2I also take common. See here, like this, ab square plus ac square, we take a square common and multiply by b square plus c square, and this a square multiply by b square plus c square. A square is a, and this b square plus c square as it is. Like this way, these terms come from this. Here see this 2I is nothing but the polar moment of inertia, and polar moment of inertia denoted as J. R by J in bracket m plus minus under root of m square plus t square. And see this and remember. What do you remember for seeing this? R by J and J by R. What is J by R? See, polar sectional modulus. Polar sectional modulus is defined as the quantity which is obtained the polar moment of inertia of the cross section of the member by the distance of extreme fiber from centroidal axis. That means polar moment of inertia divided by R is Zp, and Zp is nothing but the polar sectional modulus. So right here, J by R is Zp, and that means R by J is equal to 1 by Zp. Just calculate it mathematically. 1 by Zp, m plus minus under root of m square plus t square So from this equation, sigma maximum is equal to 1 by Zp plus m plus minus under root of m square plus t square, and minimum stress is 1 by Zp minus m. See here, only plus comes, only plus, here minus under root of m square plus t square. Now next step is equivalent bending moment. Bending moment formula is m by I is equal to sigma by y is equal to E by R. An equivalent bending moment, that means me by I is equal to, and here we use, in terms of y, we use radius because this is shaft. So me by I is equal to sigma by R, and sigma use maximum here. Now me is equal to sigma max multiplied by I divided by R. So equivalent bending moment is equal to I by R multiplied by sigma max is 1 by Zp plus here m plus. So this is equivalent bending moment. See, this sigma max, we write this because here R and 2I comes, and here see this IR comes. So I by R multiply by R by 2I. So this R, this R, this I get cancelled. Just repeat. This is not necessary, this step. After this step, directly this step, and equivalent bending moment is equal to 1 by 2 see here this is multiplication. See, we write addition. This is not addition here. This is multiplication. So 1 by 2 multiply by m plus under root of m square plus t square. So this is equivalent bending moment equation. Next is maximum shear stress. And maximum shear stress denoted as tau max. Tau max is equal to sigma max minus sigma minimum divided by 2. and sigma max is this 1 by zp plus under root of m plus minus and minus this, that means c sigma max minus sigma minimum c. When we minus this term, this zp get cancelled and this minus minus plus, only these two terms remaining. So directly we calculate it, 1 by zp plus m square plus t square. I think here also see, this is 1 by zp, here also we make mistake, this is also not plus minus, this is multiplication symbol. By seeing this above equation, see this multiplication symbol by 1 by zp. So this is minus 1 by zp multiply by m minus under root of m square plus t square. And divided by 2. See signs very carefully. 1 by zp, this is minus, so this get cancelled, multiply by m plus this m also get cancelled. So only remaining is m plus t square by zp, and that means m plus t square, 2m plus t square by 2 zp. Yes, see this m plus t square and this m plus t square, this minus minus gets plus, that means 2 under root of m square plus t square by these 2 zp. These two get cancelled, remaining is sigma maximum is maximum shear stress is under root of m square plus t square divided by zp, polar sectional modulus. Now next is equivalent torque. Torque formula is T by J is equal to G theta by L is equal to tau by R. And here for equivalent torque we use this TE, that means equivalent torque TE by J is equal to tau max by R. Te is equal to tau max multiplied by J divided by R. And tau max is under root of m square plus t square by Zp and multiply by J by R. So J by R is nothing but the Zp. So this ZP get cancelled. Remaining is m square plus t square. Equivalent torque is under root of m square plus t square, and maximum shear stress is under root of m square plus t square divided by Zp. Now one equation, remember location of principal plane. Tan 2 theta is equal to 2 tau by sigma, and this is nothing but the T by m. This equation, remember, T is torque and m is moment. So by this way, our derivation of shaft subjected to combined bending and torsion is completed. First step is bending formula, m by I is equal to sigma by y is equal to E by R. Second step is twisting moment by twisting torsional formula, T by J is equal to G theta by L is equal to tau by R. J is 2I, Zp is J by R. Zp is polar sectional modulus. It is polar moment of inertia divided by radius of that shaft. Maximum stress is 1 by Zp into m plus under root of m square plus t square, and minimum stress is 1 by Zp into m minus under root of m square plus t square. Equivalent bending moment is 1 by 2 into m plus under root of m square plus t square. And equivalent shear stress is under root of m square plus t square divided by Zp. And equivalent torque is under root of m square plus t square. And location of principal plane is tan 2 theta is equal to torsional moment divided by bending moment. Thank you very much.